It's a fairly long lecture, and it's a long activity too, so we'll try and get through as much of this as we can. That does mean I'm starting now, which means you need to stop. Okay, so Fischer Esterification is the lab you guys are going to do. You're going to make an ester. Esters are sweet-smelling compounds, typically, so you'll see them in a lot of fruits. Okay, so in this case, if you look at berries, pineapple, and pears, those compounds underneath those happen to be what make those scents, okay, or the characteristic smell from each of those. What you're going to be responsible for is looking at an ester functional group and trying to realize how it can come apart. Okay? So in the example on this slide, what we're looking at is, we'll focus on the left, looking at your starting ester, and we want to see how that ester was made. So we're going to think about it in the reverse direction. We're going to try and find the functional groups or the pieces that made up that ester. Okay? So what we can do are a couple things. One, we can compare back and forth between our reactants and products and trying to decide what changed. Or what we can go through and do, actually, yeah, we're going to go ahead and do it that way this time. Okay? So what changed? What bonds were broken? What bonds were formed? Take a guess. How about the one that has a line already drawn through it? What do you think about that bond being broken or formed? That carbon-oxygen bond was probably broken. So we can go through, draw a line through it, say that bond broke in this reaction. Were there any other bonds that broke during this reaction? Okay, so let's go ahead and continue on to what bonds were formed. So what bonds formed in our reaction? So where would we look for the bonds that were formed? Okay, well, if we look at that structure up top, what bond was formed in that structure? Okay, what we're trying to do is compare to the products in this case. Okay, so if we're going to try and identify what changed, we now need to evaluate. We looked at the bond that was broken in this case, or formed, depending on your perspective. We now need to go shift to the other side of the reaction and evaluate what changed in that case. So what bonds ultimately changed at the bottom? What bonds changed down here? Okay, there's a hydrogen-oxygen bond. Which one are you referring to? There's two of them. There's a hydrogen-oxygen bond there. That bond ended up forming
carboxylic acid right there. Right? Where the cut formed.
It's the CO bond. Yeah, that bond formed. So if we go through and evaluate, we look at the ester where you said the only bond that broke was that CO bond. So if I go through and look at that, I count carbons and oxygens, and I see 2 oxygens. I look at my product, how many oxygens do I have?
3.
If I look down here, how many oxygens do I have? 3. So could that have been the only bond that was broken? There had to be another bond. Where is that other bond that was broken? The hydrogen-oxygen in our water molecule. So the idea is to track down those bonds that are changing, because once you've identified the changes, you can start to predict how that reaction is going to occur, how you can put it together. Okay? If we looked at the example to the right, we didn't actually provide the carboxylic acid. What would the structure of the carboxylic acid be? Well, if we look to the left, our carboxylic acid was the one highlighted in blue there, right? Okay, that piece came from that part of the ester. So what can we do? We can just draw out the structure of that piece. Plus, what else had to form on that? We needed that OH bond. Okay? Let's look at a different way to solve these. Instead of now looking at reactants and products, or looking at 2 sides of the equation, what we're going to focus on is now just looking at a single structure, or single side of it, and trying to predict what occurred. Okay? We could have it memorized from before what things were broken and formed. Or what we could do is start to evaluate our structures and try and find positives and negatives. Because if we can find those positive and negatives, believe it or not, it solves our answer for us. We don't have to know anything about the chemistry. So let's take a look. Which species do you want to look at, water or your ester? There's no wrong answer. Give me one. Okay, sorry, I heard enough esters. Okay, so let's move to the ester. We need to find partial charges, because that's where our reactivity is. Where do we have partial charges in that structure? We're going to have partial charges wherever we have differences in electronegativity. So we can take a look at those oxygens. What's special about oxygen? It's highly electronegative, meaning what's it do to the electrons in the bonds near it? Pulls towards it. So we get a partial negative and a partial negative. Okay? What does that mean to the carbon that's now attached to those two oxygens? It's now extremely partially positive. Okay, why extremely? There's two electronegative oxygens attached to it. Okay, so if we're going to look at our reactivity, we've found our positive. There's only one really big partial positive. Between those two oxygens, okay, or rather the oxygen-carbon bonds, which one's going to be the easier to get rid of? Why the single-bonded one? Okay, it's easier to break one bond than it is to break two bonds, which means more than likely our largest positive or our largest negative, our reactive oxygen, is going to be this one. So we've got a partial negative and a partial positive. How could we stabilize those? How do you stabilize a partial positive?
Partial negative.
Give it some electrons. So we could look to our solvent to try and stabilize these. We're trying to run a reaction, so let's see if we've got another partial positive, partial negative somewhere else. Do we have another reagent? Water. Is there a partial positive and partial negative within water? Yes. Where are those? Our H is positive and our oxygen is negative. Why? Difference in electronegativity. Okay? So if we're now expected to predict our products in this reaction, what we're going to go through and do is take the positive from one structure and match it up with the negative of the other structure. Okay? It seems stupidly simple, but it amazingly works with 90% of the chemistry you're going to see this semester. Find the largest positive, find the largest negative. And if we were asked to draw these, we would end up with this structure is our carboxylic acid, and our alcohol would be that guy. Okay? So, again, we don't have, and you're not responsible for the mechanism for how this occurs. What you're responsible for is identifying where the bonds are easiest to break and form and to shift to form one way or the other. Okay? So if we continue on, we can look at what you're going to do in lab. You're going to take acetic acid and you're going to react that with an alcohol. Okay? Because that would make the lab only smell like particular fruits, we're going to turn it into a fruit cocktail, and you're going to end up making a ton of different esters. Okay? And by a ton, I think 5. So your TA will assign you a different alcohol for each group. Each of those groups will then make their own ester, and then you can make your observations, sense, all that kind of fun stuff with the alcohol, okay, or with your ester product. Okay? So we can write out a generic reaction because you don't know what alcohol you're going to be given. So that's what our top line is for, okay, to represent overall what you're going to be running in the overall reaction. Okay? What's our mole-to-mole ratio through that? 1 to 1. Okay? So if we were going to go through and calculate limiting reagents, our mole-to-mole ratio that we would use is just 1 to 1. Okay? If we look at that R, what does that R stand for? Some functional group. Okay? So the R's are assigned down below. What we're changing is the number of carbon chains, or the number of carbons in the chain and how those atoms are arranged, and that's going to strongly change the smell of the ester. Okay? What's that squiggly line mean? Not quite. It's where your R group is. It's where that group attaches to the alcohol. So to make these each our alcohol, we could say OH. OH. All we're doing is adding it at that point. Okay? Just so you're aware. That's kind of a gimpy looking O, but it works. Okay, so now we can go through and identify the roles of each of our compounds. Okay, so typically when we run reactions, we use a solvent. Okay, what's the role of the solvent? To dissolve your compounds. Okay, so that they can interact with each other. That makes sense, that works. So what's your solvent in this reaction? So H2SO4 is not a bad option, okay? Except how many or how much sulfuric acid are you using in this reaction? Not much at all. In fact, you're using 1 to 2 drops. How often or what scale are we working in where 1 to 2 drops is going to dissolve everything? Probably not the greatest. Okay, so sulfuric acid's out. Okay, what other solvent are we adding to this? We aren't adding water, and we'll talk about that important too. Okay, we could say the alcohol. I'm hearing kind of 50-50 here. Alcohol or acetic acid. How do you know which one's the solvent? Both of those are reagents. We're actually using those as chemicals, okay? Or using those as compounds within our reaction. So they're better classified as a reagent. So what's our solvent then? Well, that's where it gets tricky. Okay, the answer that I would give for this is your solvent is, see if you guys can figure it out as I write. No, not really. Solventless. There really isn't a strict solvent in this case because we can better classify everything else as a reagent. If you're forced to assign one of these as a solvent, which one should you assign as the solvent? Okay, it is acetic acid. Why acetic acid? Okay, I'm pretty sure, and you need to check your reaction or your conditions just to make sure, it's the one that's in there in the largest concentration. Oh, thought that no was at me. Okay, so yeah, that's the one that's in there in your largest concentration. That one can act as our solvent if we're forced to call it that. Okay, why do we not need to add a third compound to this to act as a solvent? What phase is acetic acid? Liquid. What phase is the alcohol? A liquid. Everything's already a liquid. We don't need to put it into solution to get them to mix. These compounds are already going to mix on their own. Okay, what's the role of sulfuric acid now? It's going to be the acid catalyst. Okay, so it's there to change the mechanism to speed our reaction along. As far as the limiting reagent, how would you figure that out? You'd have to go through and determine what compound was in there in the lowest amount, and you'd be determining acetic acid or your alcohol as your limiting reagent. I just told you that the acetic acid is in there in a larger concentration, so we might expect that it's going to be our excess reagent. Okay, but you need to run through those calculations. As far as preparing for the lab, most of you have had your TAs tell you need to have a limiting reagent calculation completed already. Well, it's very difficult to do if you don't know what your alcohol is. Okay? You don't know the molecular weight of your alcohol or of your ester to be able to figure out your limiting reagent. So what should you do? Pick one. Pick one and circle or identify the point that's going to change. Okay? And then look up the molecular weight, which is the only thing that's going to change for those, for all the possible compounds. That way, when you get into class, and if you're assigned one of the other alcohols, you can quickly change your calculation and get your answer relatively speedily, as opposed to taking forever to figure it all out again. Okay? What does your product look like? Okay, we just looked at possibilities. We looked at the reverse for this. We're going to take your acid and react it with our alcohol. So let's pick one of those alcohols. Okay, what would the product be if we react acetic acid with this compound? And as simple as a question as this may sound, it ends up being a lot trickier because most people will forget certain things. So let's start with our acetic acid. What's attached to the carbon of our carbonyl? If it was acetic acid, it would be OH, but we're trying to draw our product. It would be an oxygen. Where did that oxygen come from? The alcohol. So we can draw that in red so we can see it a little bit better. What else is that oxygen attached to? Okay, the hydrogen's ultimately going to come off the carbon chain. So what we need to then do is draw the bond to that carbon. Where is this carbon in my starting material? This one right there. Okay, what else is that carbon attached to? Two other carbons. And technically a hydrogen. Okay? Yes, got it there. Okay? More often than not, students will forget a carbon. Okay? Because it's a point, we tend to ignore it. How can you make sure that you don't forget carbons? Okay? You can make sure that you label each of those, which is a lot of work. You could count carbons in your reactants and products. If the carbon count changes, what does that mean? You forgot one. Go back and check. The other way is to go through exactly as I just stated here. Track one for one where every single atom was connected. And if you don't change the bonds around it, don't start changing them in your product. Okay? So if we look closer at our reaction, we can look at, say, the equilibrium constant, which everybody remembers from second semester Gen Chem, how much fun that was. Okay? And in this case, the equilibrium constant for this reaction is 1. Okay? What does that mean for us? What can we correlate the equilibrium constant to? Whoops, don't do that. You didn't see that. No. I said you didn't see that. You're wrong. That's not what I asked. We can correlate it to energy or a reaction energy diagram. Okay, so we could look at our reaction coordinate. Okay, if our our equilibrium constant is close to 1, what does that mean about the energy of our reactants in comparison to our products? They're roughly the same. So if we looked at our reactants and our products here, whoops. Okay, we would end up saying they're the same energy. What does that mean about the driving force? There isn't one. There is no driving force for this reaction to occur. Well, if we're going to try and make our ester in high yield, we need to make a lot of product. If there's no driving force, we need to somehow change our reaction conditions, adjust them so that we can maximize the yield of our product. Okay? How can we do that? Now you can answer. Le Chatelier's principle. We can go back to that funny French man or woman. I actually don't know. Okay? So if the equilibrium is disturbed, it's going to adjust to account or negate that disturbance. Okay? So let's look at some possible things that we could do to change our reaction to try and make more product. Okay? So what happens if we add heat? What does adding heat do to a reaction? Okay, it speeds it up. Does it favor one direction or another? Depends on if it's exo or endothermic. Do we specify any heat transfer in this reaction? No. So do we know which direction it favors? No. So what does it do for us? Oh, come back here. All it's going to do is speed up our reaction. Okay? Or you could say it catalyzes it. Okay? What happens if we add an excess of the alcohol? So if we put in a 1-to-1 ratio, we'd expect everything to even out as far as concentrations. What happens if we add more alcohol? It's going to push towards more products. So we would expect products to be favored. What happens if we use water as the solvent? Remember, somebody said something about using water as a solvent. Water is one of your products. If we used water as a solvent, what happens to our yield of ester? It goes down. Okay? So adding water favors our reactants. What happens if we distill the product? What does that mean? What are we doing if we distill the product? Boiling it away. We're taking our product, we're turning it into a gas, and removing it from the reaction. If we remove product, what does that do to our equilibrium? Favors to forming more products. Okay? What happens if we add more sulfuric acid?
Absolutely nothing.
Nothing. Okay? It's a catalyst. It's not going to have any effect on our reaction. Okay? As far as the reaction conditions, we'll add heat to our reaction, but we mentioned a problem with this. Your product has a lower boiling point, which would mean if we just heat this reaction up, what happens to your product? Boils away, turns into a gas, disappears. We don't have product anymore. Okay, so what we're going to do to maintain heat in our reaction but not lose any of our compounds, either our products or starting materials, is we're going to do something called reflux. Okay? And just like acid reflux, what it's going to do is trap liquids inside it. Okay? So your gas or your, whoops, come back here. How did that happen? Your liquids are going to turn into a gas. Those gases rise up inside the column. Okay? That piece of equipment is your your jacketed condenser, okay, where it's going to have water pumping through it. What temperature is water coming out of the tap typically? Usually cold. So what's it going to do to the glass? It's going to make it cold. What happens when our vapors touch the cold glass?
And then shatter, possible.
No.
Sorry, I was thinking thermal.
There's too much of a change there, so no. It's going to condense, go really simple. We now have liquid on the side of a vertical piece of glass. What does that liquid do? Drips back down into the reaction. So we can maintain heat in the reaction and maintain volume at the same time when running a reflux. Okay? So it's kind of a helpful technique as far as this goes. After the reflux, we've reacted it long enough, we need to go through and isolate your product. Okay? You've got a bunch of different things in there that contaminate your product. You've got unreacted starting material, you've got sulfuric acid, you've got your product, you've got water, and then you've got whatever else could possibly occur during the reaction. Okay? And you sometimes get a lot of that junk going on. We need to come up with some way to separate all of those. The first thing that we're going to do is add bicarbonate. Okay? Aqueous bicarbonate. What is bicarbonate? HCO3 acts as a base. Okay? Can act as a buffer in particular conditions. So we're adding a base in this case, a water-soluble base. So we're going to see two layers form. You've got your organic product, which is going to be relatively water-insoluble. No hydrogen bonding. Okay? We just have dipole-dipole forces and a lot of alkyl trace or structure to it. So it's going to be insoluble in that layer. Okay? So what's going to happen? You're going to see two layers. You're going to remove the water layer. Now it's gone. Okay? And that's where we've got what's occurring on the left over here. Or that's my right. Let's try that again. Okay? We're just pipetting that away. What do we do with the organic layer? It's still going to have some trace water in it. How can we get rid of the trace water? We can add a drying agent, which is the role of sodium sulfate. The drying agent will wrap around individual water molecules, forming a nice, easy separatable solid. We'll then be left with isopenyl acetate and our high boiling impurities. Okay? How can we get our product? Our very last step is going to be distillation, okay, to get your final product. So, if we had to come up with some way to separate these three compounds using an extraction technique, so that's what we just walked through, what could we do? What is NaOH? It's a base, a particular strong base. What's that next one? Can't see it. NaHCO3. It's also a base, happens to be a weak base. What do weak bases react with? Strong acids. They can't react with weak acids. What do strong bases react with? All acids. Okay? HCl is strong acid. And sodium sulfate, it's a really weak, or actually it's not even an acid. We don't have hydrogen ions on sodium sulfate to have it act as an acid. So it can't be an acid. It's a really, really weak base, so weak that we don't say it even acts as a base. So why is it there? Someone said it. That's our drying agent. Okay? Why is it on this list? Confusion. That's it. So we now have some reactivity of each of those compounds, so we could go through and look at our unknowns. What functional group is that?
Carboxylic acid.
Carboxylic what?
Acid.
What do acids react with?
Bases.
Bases. So what happens if we add a base to this? It reacts. What happens to the structure? Changes. What happens to its solubility once it's changed in water? If it reacts, we form what charge is that? Negative. What do we refer to negative charges as? Anions. As a class, what kind of, how would we refer to that? How about ions? What kind of force do we get there? Ionic. What kind of compounds are ionic? Salts. What do we know about salts? Highly soluble in water. Okay? So when we add a base, it changes the structure and makes it water soluble. Okay? What is that base going to react with? What do bases react with? Acids. Is this functional group an acid? Is this functional group an acid? No. So what happens when I add base? It only reacts with compound A, and it only changes the structure of compound A. That compound shifts into a water layer. What happens to the other two? Absolutely nothing. They stay in the organic layer. Okay? It's the idea on how you should be processing these extraction protocols. When it comes back to your reaction, you'll have it heated up. You're going to cool that down and then add aqueous bicarbonate. The bicarbonate will react with the acids present, changes the solubility, allows you to purify or separate the two compounds based on solubility. One thing to watch out for, bicarbonate, when it reacts with acid, forms what? Carbon dioxide, which is what phase? A gas. You can see this reaction fizz an awful lot. If you don't cool it down, it may actually spit chemicals all over the place. Okay? So cool it down a little bit. Watch out for it. Don't just cap it right away, because you can start creating mini explosions. Okay? How can you remove that aqueous layer? You can use a pipette, which is what that drawing is showing. I think it actually looks pretty cool. Once we remove that aqueous layer, what are we going to be left with? You'll have your ester, some impurities, and maybe a little bit of water left. Okay? The little bit of water left should be invisible to the naked eye. Okay? If you can see it, you should be pipetting it out. How can we get rid of the last dregs of water? That's where we can add our drying agent. How much drying agent should you add? Enough. Why is it enough? Why can we not say exactly how much to add? Don't know how much water was there. Okay? How do you know you've added enough drying agent? Till it's dry. What is dry? Not wet. What is wet? No, it's water. It's no water present, but we just said before you added the drying agent that you couldn't see water. How do you know you've added enough drying agent? The drying agent must look, a small excess of the drying agent must look the same in the liquid as it does in the bottle that you got it from. Okay? In the bottle, it's anhydrous. There's no water present. So it should be a nice free-flowing kind of powder, depending on what drying agent you've got. Okay? If you put it into your solution, it's going to clump around water. If there's no water present, what's it going to do? Stay powder. Okay? Once you've got the drying agent in there, you can now remove it. You can do that either through filtration or decanting. Decanting is probably going to be your easiest and best option. You'll now have your ester product and then your impurities. You won't need to evaporate any solvents because you shouldn't be adding any other solvents to this. And then you can go through and distill. Your impurities, we're hoping, have a really high boiling point, so you won't have to stress about those. And your ester will distill out of it. To set up the distillation, very similar to your reflux, we're going to heat our liquid down at the bottom. What happens to the liquid? Turns into a gas. That gas rises up inside the column until it hits Our cold glass. What happens when it hits the cold glass? It condenses, and it does what? Drips back down. And if it dripped back down back into the reaction, would we ever collect it? No. So what has to happen? We put a Hickman distillation head. That little distillation head has a little lip on it. Your liquid is going to collect right at the base of that. Your job is to pipette the liquid out through that side port before it drips back down into the reaction. Okay? So if we were looking at some compounds and we wanted to figure out which one would be the first or second to collect in the Hickman head, what does the Hickman head separate based on? Boiling point. How do we determine boiling points? Intermolecular forces. So what we can go through and do to answer this question is specify the intermolecular forces on each of those compounds. You can go ahead and pass out the group activity. Okay, which of those has the strongest intermolecular force? The hydrogen bonding, which is C. Which has the weakest? B. Which one has the highest boiling point? Highest boiling point means it requires more energy, which would mean strongest intermolecular forces. So we're looking at our highest boiling point here. What's going to have our lowest boiling point? B. Which compound is going to be the first to collect in the Hickman head? B, with the lowest boiling point. Which one's going to be the last? C. Once you've got your product, you can then go through, determine your percent yield. You can record a rough approximate boiling point using your Hickman distillation head. It probably won't work, but you're going to do it anyway. And then you'll obtain an IR of your starting compound and your product. What would you expect to see in the IR? Ester has at least 3 bonds. So telling me you expect to see an ester functional group in the IR is not a very good sign for your IR assignment that you just turned in. The carbon-oxygen double bond. The carbon-oxygen single bond, where does that show up? In the fingerprint region, so you aren't expected to see that. Is that carbon-oxygen double bond going to be particularly useful to identify your compound? No, why not? Where else do you have a carbon-oxygen double bond? In your starting material. So seeing the carbon-oxygen double bond does not confirm your product. And we don't have any other bonds to confirm it. So what are we going to use IR to do? Confirm the lack of starting material. What peak do we expect to not see? You shouldn't expect to see water, that's true. There's a better one. What was your starting material? An alcohol. We would not expect to see the OH peak. Okay? At the end of that, you just clean up. If you got questions about the group activity, raise your hand and ask. I will comment a couple things here. I try to give you some clues. Your very first question, benzoic acid, or the very first question on that sheet asks what you should add to separate those. Okay? If you take a look to the left, it's drawing the product of that reaction. Okay? That product came from what compound? Did it come from toluene? Okay, well, you're not listening, so that's fine. Go ahead and continue with the activity. If you got questions, good luck.